Hi everyone, we are Jaho and Brian. Today we're going to talk about hacking blind, which is blind return-oriented programming or BROP. So before we talk about this fascinating technique, please let me briefly talk about the history of buffer overflow. The two forces, offense and defense in computer security, leads to various techniques in this area. The most intuitive exploit is probably shellcode injection, in which we put our shellcode into the stack and return to the stack. As a defense, the stack is said to be not executable for writable spaces. Then the offense team decided not to return to stack, but to library, to syscall, etc. Later, the defense team find the address space layout randomization technique, which is ASLR, and this will give you a different address each time you execute a program. Therefore, it makes it harder for the attackers to actually get the return address. However, the offense team used the information leakage to actually detect those addresses and use offset to compute the address at the runtime. This information leakage also defeats the canary value, which is a value between the buffer and the actual return address to prevent the hacker to rewrite those addresses. So why is the BROP so important? As we know before, the non-executable stack requires a vulnerable binary available for you, and the address space layout randomization needs information leak or statically positioned code, which sometimes may be hard to find. The ROP provides us with a great way to actually hack a binary without knowing the binary file itself. It actually defeats the NX and also defeats the ASLR in position-independent executables with no re-randomization. All we need is one bit, whether the server crash or not. The BROP is used in the following three scenarios. First, proprietary closed binary services. Also, open source library used in proprietary closed binary service. And the last one, open source server with unknown binary. What do we have? All we have is a server. So how should we do it? The attack outline is first, stack reading, second, blind ROP, third, build the exploit. Okay, so let's talk about the stack reading ASLR de-randomization. We all know there is canary value between the buffer and also the RBP. Therefore, we just write the buffer with us and then to see if there is any value that will make the server not crash. That will be the correct byte. So it's similar to what we did in class. It's like you changing those combinations into linear time. So you're changing one byte by byte, and then to see which one is actually the correct value. Eventually, we get the canary value. And also we can use the same technique for the RIP to get a valid return address in this binary. Therefore, these information will be leaked out as we go. Right now, what do we have? We know there is a buffer overflow here, and we know there is a valid address in the .text segment that we can use later.
In general, having a control over RDX isn't necessary, but pop RDX return is a rare gadget. In order to gain control over the RDX gadget, we need to find and call to string compare instead. String compare sets RDX to the length of string getting compared. Therefore, to complete the attack efficiently, we need to get BROP gadget and procedure linking table. With PLT, we get the entry for write and string compare calls. To find gadgets, we scan the application's text segment by overriding the saved return address with an address pointing to the text and inspecting program behavior. We can start from the initial stack or OX400000 on default NumPy Linux. There'll be two behaviors we can observe, crash or no crash. If we find a valid position where we face an infinite loop, we can keep the connection open. We can utilize both crash and non-crash addresses. We're going to use the address without crash as a stop gadget. We need to use stop gadgets because even if we find a useful gadget, as we return to this next word in stack, it will crash. Thus, we put the stop gadgets in the stack upon finding useful gadgets. The above cell will crash as it returns to the null address that be. The bottom stack shows the implementation with stop gadgets. Upon returning to the stack, it will not crash, knowing we found a useful gadget. Now we know how to find useful gadgets. We need to determine kinds of gadgets we found. Probe is the address of gadget scanned. Stop is the address of gadget that doesn't crash. Trap is the address of gadget that crashes. Putting stop and trap on various positions, we can figure out the instruction executed by gadget. In this specific diagram, we're looking for a return gadget. The stack above is a pop gadget, which will return to the stop address. However, because the bottom stack isn't a pop gadget, it will return to a trap, causing the program to crash. We can observe crash and non-crash behaviors with different combinations of probe, trap, and stop. We know how to identify gadgets, and we can now search for the BROP gadget. On the right side, these are gadgets that we need for write and string compare, and we can obtain pop RDI and pop RSI from BROP gadgets. The left side is the BROP gadget we need. If parsed at offset 0x7, it gives pop RSI, and if parsed at offset 0x9, it yields pop RDI. In order to find the BROP gadget, we can utilize the identifying gadget techniques from previous slides. If we order the stack as probe, stop, traps, and so on, we can find gadgets like return or XOR, RAX, return. If we place as probe 6 stops and trap, we can now identify the BROP gadget. We have identified the BROP gadget now, and we can move on to finding the PLT. A procedure linking table, PLT, is a jump table at the beginning of the executable for external calls. This means that a call to a library call will be a call to PLT, which dereferences the global offset table, GOT, and jump to the address in GOT. PLT does not crash easily, and therefore we can find the PLT more easily. We need to scan PLT and find string compare. We are going to use two input parameters, bad as an invalid memory and readable as a readable pointer. String compare will show different behavior for different input parameters. We can use BROP gadget, which controls the first two arguments. Using this technique, when we don't see a crash, we end up with a string compare. Once string compare is found, we can set the RDX to a non-zero value by giving a pointer to PLT entry or the start of the ELF header, which has 7 non-zero bytes. We'll show you a demo of what we have covered so far.
So right now we've already set up a server that has our binary file, and right now we can use the IP address and the port to access the server. So the first thing we want to do is basically to check whether there is a Stack Overflow vulnerability there. So we'll use our size script to do this. So first of all, our most well-known technique. So we're adding the A's into our buffer to actually see whether there is a buffer overflow. And here you can see we're actually adding the size, and to see to which size we can actually access the RIP or the return address register. So as we can see now, the buffer size is actually 72 minus 8. And since there's 8-bit, so we actually need 72 bytes right before we reaching the RIP or the return address register. Then we run a script to find our stop gadget. So we're starting probing from 40000, which is the beginning of our ELF. Since I've already run this script, we can see the stop gadget is actually at 400585, and we can use this to actually find our BROP gadget. So how do we get our BROP gadget? Basically, we have our stop address, and then the BROP gadget has a very clear signature of 6 pops. So we set 6 traps here, and then there's the stop. So if it is the BROP gadget, then it will be halting the server. However, there is another kind of gadget that will also satisfy this condition, which is the stop gadget. Since the stop gadget will go to another address and not crash the server. Therefore, we change this stop to trap here, such that the stop gadget will not be considered as the BROP gadget, since in this case, it has to fail. So right now, we've finished running the BROP gadget finding function, and the BROP address of the BROP gadget is actually 40078. So right now we have our BROP address, and next step is to check the PLT table. PLT table has a very clear signature because all the entries are 16 bytes away, and all these entries will not crash the server. Therefore, we're creating a for loop here to say, okay, once I have an address, check all the addresses following it that's 16 bytes apart. And all I need is 4 consecutive addresses that do not crash the server 16 bytes away, and I will think they are the PLT entries. So right now, as we can see, the address of the PLT entry is 0x4005CO. Okay, this is our strcmp function that's used to search which entry is actually the string comparison function. Since the comparison function will only not crashing the server when it has two good addresses. And this is a very unique feature. So we actually use this one to say all the functions that fit this feature will be considered as our comparison function. There we go. Right now we have the address of the strcmp function, which is at 4005do.
The full exploit or spawning a shell is not available at the moment, but we only have a few more steps left. We now have a control over the first two arguments with BROP gadget and the third argument with string compare. Write can trivially be found scanning each PLT entry and forcing a write to the socket and checking whether the write occurred. We need to determine the 5 descriptor number and can utilize the two approaches. The first is chaining multiple writes with different file descriptor numbers, and the second is opening multiple connections and using high file descriptor numbers. A combination of the two will be used since Linux has a minimum of 1024 simultaneously open file descriptors, and POSIX requires new descriptor to use the lowest number. We have the last part to conclude the attack. We'll need to redirect socket to standard input output and find BNSH in the memory and execute the cell. But how do we defend against the attack? In order to prevent against BROP, the author of Hacking Blind suggested 4 methods. Re-randomization is the most basic protection and is re-randomizing canaries and ASLR as often as possible. So the simplest way is to fork and execute the process on crash and spawn. This re-randomizes both canaries and ASLR. Sleep on crash is delaying a fork after the segmentation faults. This will slow down the attacks, but the downside is that bugs can become easy denial of service attacks. Meanwhile, if you put 30 seconds delay and assuming BROP attack can complete in 1,000 requests, this will delay attack by roughly 8 hours. RP protections like control flow integrity could prevent RP in general by enforcing the control flow graph. Lastly, modern compilers insert runtime bound checks on buffers, which could also prevent bugs.